Hello everyone and welcome back. So now let's try a group problem. So as always, I suggest that you bring in a friend. Maybe a rubber duck. Here, I'll give you a friend today. This is your friend, rubber duck friend. Okay, he's gonna be amazing. There we go. Yes, there we go. So here's your rubber duck. I'll even give it a little vest and a bow tie. Perfect. And let him help you in this problem if you're feeling a bit anxious. So, what do we have here? Well, you have a sports car. It's going up a hill, and it's increasing its speed uniformly from rest to 25 meters per second in 30 seconds. That uniformly word, for some reason I've both changed its color and underlined it. The engine's efficiency is going to be 0.8. What do we want to find? We want to find the maximum power and the average power supplied by the engine. Max power and average power supplied by the engine. Are they the same thing? I don't know. We got to figure that out. So, what's your plan? Well, your plan is this. Draw the car's free body and kinetic diagrams. Apply the equations of motion and kinematic equations to find the force. Determine the output power required, and then use the energy efficiency to determine input power. Okay, now with that in mind, pause, go try it out. May the duck be with you, and I'll see you all soon. Give it a little monocle too. There we go. That's beautiful. So, have fun. I'll see you in a second or two. So, 3, 2, 1, and you're back. Hopefully the duck was able to help you. If not, he's not that good at math. Maybe we'll go do it together. So what we're going to do first, well, we're going to draw a free body diagram and kinetic diagram of the car as a particle. It's a particle because I don't care about its size. Size isn't helping me here. So what do we have? Well, let's see. We have the weight of the car pulling us down. We have the force of the engine, which is pushing us up the hill. We have the normal force also from the hill pushing us up. And that's causing some acceleration, though. Imbalanced forces are causing us some acceleration up the hill. Now, the normal force and this frictional force right here from the car, well, that's coming from all the wheels. The wheels are turning, they have to grip the ground, and that's then pushing them up the hill. Okay, that's pushing them up the hill. So, one question to ask yourself in this case is, what are we neglecting in this? What force are we neglecting with this approach? Drag. We're not bringing into any drag. There would be wind resistance, but we're ignoring that for the moment. We're just pretending like, this doesn't exist. This poor person who's in a convertible, he is driving through a vacuum. Okay, so now we solve our equations of motion. So we pull it in here. We have some forces in the x direction equal to our mass times acceleration. There's only two things pointing in our x direction, which is going up the hill. That's my frictional force from the wheels pushing on the ground. And my weight. My weight is also going to have a component in the x direction because x is going up the hill. X is not directly horizontal. You can make it directly horizontal, but then it makes things a bit more difficult. So we avoided that. Now where does this 5.711 come from? That is simply from my slope. Now, I don't actually know what my acceleration is. However, I can use my kinematics. Yes, kinematics. They never go away. Ever, ever, ever. I'm going to use my kinematics to solve this. So I know that it accelerates at a constant rate. And so my acceleration will simply be my change in velocity over the time, or 8.333 meters per second squared. So with that knowledge, I plug it into my equation. And what do I get? Well, I get that the force of friction from the four tires is 3,619 newtons propelling me forward. Now, obviously, that force comes from the engine. And I asked for two things. I asked for the max and the average power output. So the max power output is going to come when I am going at the max velocity. So I'll have my 3,619 newtons of force multiplied by the velocity of the car at its max velocity, which is 25 meters per second, which is going to come out to be 90.47 kilowatts. 90.47 kilowatts. K there means 1,000, so 90,000 470 watts. The average power would be equal to my force times the average velocity, which is, since it's accelerating at a constant rate, would be 25/2. If it did not accelerate at a constant rate, if it changed for some reason, and my velocity was not going up at a linear rate, I would have to find more or less the centroid of this velocity distribution. You could take the area and you could just find a point where there's half the area on one side and half the area on the other. I'm not going to do that for you for a while, but just remember that the average velocity won't always be so simple to calculate. Now, the power supplied by the engine is neither of these. This is the power out of the engine, okay? Or in this case, since the engine we're saying is perfectly efficient, this is the power that makes it through the car from the engine and into the ground. But once it's being transferred by all those shafts and gears, it loses some energy. And so the power actually supplied by the engine would have to be greater than this power. So we would have a max power output from my engine of 113 kilowatts and a max power output on average of 56.5 kilowatts. And as a note, because the engine is in itself inefficient, we'd have to use even more, get more power from the fuel that we're burning. So it's just stair-stepping of efficiency. We keep on losing energy as we go. So the fewer steps, the more efficient your system, because you're not having any sort of multiplicative losses. So that's it for this one. Thank you for listening, and I'll see you all next time. Bye-bye.